Yes, obviously I'm not Bernhard Rumpe, so yeah. I'm Nico from RWTH, and as already introduced, I want to talk with you about compositional model interpreters. So just as a context, when we do something at our chair, we do this within the context of our language workbench MontiCore. So just in case you don't know it, a very brief introduction. This is the language workbench for developing textual DSLs. We are developing since, I think, almost 20 years by now. And what MontiCore provides is a lot of infrastructure for additional model analysis, for transformations and pretty printing and so on. One critical aspect which we are especially proud of is our way of composing languages. So when we develop new languages with MontiCore, we are almost never developing them from scratch. We are reusing a lot. So usually the new language only consists of a few productions and everything else is incorporated. If you already know us, well, we're the guys who throw a symbol table at each problem to solve it. If you don't know us, MontiCore, based on a context-free grammar, generates you lots of stuff for, well, obvious stuff like a parser, abstract syntax classes, so basic things for processing a model, but also a symbol table for efficient cross-navigation and cross-referencing, visitor infrastructure for, well, traversing the ASTN symbol table, also an infrastructure for additional well-formedness checks. We call them context conditions, or COCOs for short. And of course, an infrastructure for generating code. Okay, what I already told you is we have a specific focus on compositional language design. And what you see here is only an excerpt of a pretty large language library we built up over the time. So here we have several language components, for example, covering different aspects like literals, expressions, statements, types, and so on, and also with different well, levels of sophistication, you can say. So the basic idea is when you develop a new language, you choose whatever of these building blocks you want and plug them together inside your own language. For example, you want to have pretty basic literals together with common expressions, but full-blown generic types for what reason ever. You can do so with MontiCore. You just incorporate the language components and build your own language kind of only as a wrapper around it, and you're good to go. That said, we actually did this, so we developed different languages in, well, we call them 3 waves. So the first wave down here, I already explained to you. These are our language components. So the expressions, literals, statements, and so on, I just showed you. The second wave was developing known languages, class diagrams, feature diagrams, OCL, all that stuff, just by using these building blocks. And then we got even further using, well, the languages components of wave 1 and the languages of wave 2, just to build more sophisticated languages or full-blown language families. For example, UML, we have a component and connector language we call MontiArc. We even support the current standard of SysML v2 by incorporating lots of our grammars here. Of course, sometimes when you follow such a specification, not everything is a perfect match, but if 99% match, you're good to go. So you're pretty close, and the rest you can just implement or override in your grammar yourself. Okay, that's about MontiCore. I talked a lot about how we can compose languages. Now I want to show a brief example what we actually mean by this. And for those who know my talks, you most likely have seen the next this slide and the next. So starting from a pretty basic language here just for automata, yeah. What can you do? You can model states. In this case, it's a ping pong automata, 2 states, ping and pong. You have 2 transitions, well, for returning the ball from ping to pong and vice versa. Nothing too serious here. But now you might think, okay, usually when I'm having an automata, well, this is fine. Maybe I want to add some action when firing a transition. For example, counting the strokes, how often the ball is returned or something like that. In MontiCore, while we use the language as is up here, so the automaton language, we would extend it by adding whatever we need for the transitions. So just adding, for example here, the slash for indicating that an action takes place, and then incrementing the strokes by this plus plus expression. And you could do this, but what you already heard just by how I pronounce it, the plus plus or increment expression, you wouldn't do this, because what you can do is you can use a library for that. So you could incorporate the expression language component, which actually has this kind of increment expressions. So actually what you would do is start from your basic grammar, extend it, add, well, this mere slash there for syntactic sugar, and then incorporate the other grammar to say, okay, here whatever expression you want can follow, in this case the increment expression. And this is the way we build our languages. Okay, but this is of course just the front end of a language, so the concrete and abstract syntax. Usually we want to do something with our models, and for those who know who know what I'm working on, usually I'm composing all the stuff I get my hands on. 2 years ago at Langdev, I had a talk about how to compose generators. Well, there is another way of getting behavior inside our world. It's interpreters. So now I'm having a talk about how to compose the interpreters. And basically, the main idea of the interpreters is not new, and I also copied a lot of stuff. So basically from this book with lots of authors, some of which are regular Langdev attendants. So the main idea is from there. I just added the automatic functionality of composition. So again, just start from our automaton example because it's pretty easy. Here we have a representation how we actually build the language. So here we have our base automaton language incorporating several other sub-languages, 2 types of expressions and variable declaration statements. Why is that? Well, if we think of our automaton like here, the language elements that belong exclusively to the automaton are quite rare. So what do we have? We have states and transition. Maybe an additional marker for indicating final and initial state, but that's it. So everything else we see here, like a guard or the actions, or even the accessing of a variable here, are all part of these sub-languages. There might be even more. This is just for demonstration purposes. So now, when we construct our language in this compositional way, we of course also would like to automatically compose our interpreters in this way. So actually, we only, as the developer of the automaton language, only want to take care of how to deal with states and transitions. Everything else, every expression, action, whatever, should be done by incorporating the sub-interpreters of these respective sub-languages. And well, this is actually what we did. So here, just as a simplification, we only go for the automaton language and one sub-language. It's just more of the same, but it doesn't fit on the slide. So what we do is actually starting up here, having the model interpreter interface. This is basically what's described in the book I showed you before. So you have a basic interface for interpreting, and the model interpreter is built in terms of a visitor. So just a visitor traversing the whole AST. The difference is here, or the specific thing is here, that you have some kind of return value, which if you think about it in terms of an interpreter makes quite sense, because if I have an expression 5 plus 4, well, I want to return 9 to whatever step just called me. So this is the method you have here for an arbitrary AST node. Later on the language level, you refine this for each production. Then additionally, you have 2 additional methods to store a value and load a value for a respective symbol. Well, that's basically if you have a variable in your language, then you want to assign a value and access it later on. That's all. And what we do now is generate these 2 things, so one interface and one class for each of our sub-languages. So here for the automaton and for the common expressions. Of course, as I said before, also for the others, it's just a simplification. So what we do here, we have the interface which provides the interpret method signatures for exactly the productions or the non-terminals we have inside our automaton language. So the automaton itself, the read node, then the states and the transitions. So this is what we actually have to implement to show, okay, this is the behavior, how to understand the interpreter. For the common expressions, it provides respectively all the interpret methods for the non-terminals defined there. So the plus expression, the multiplication, there are many more. I think there are around 20 expressions inside this grammar. So all these methods are provided there and also are implemented there in the respective class. So you don't want to implement them anymore. You only implement this as the developer of the automaton language, and then everything is incorporated automatically. And this incorporation is also generated by MontiCore. So what we do is we employ something which is called the real this pattern. Basically, it's when you have a bunch of composed objects, you just expose them to the exterior world as one object by having one delegating or one orchestration object. In this case, it would be the automaton interpreter, just because it's the base language we are working on. So all the AST is communicating or interacting with this automaton interpreter. And for example, once we reach an expression, the automaton interpreter just delegates this call to the common expressions interpreter, which then does the computation and returns everything. And every time the common expression interpreter goes further, so maybe further sub-elements, which might not be part of this expression language, it just returns the call to the orchestrator, so the automaton interpreter, which then delegates again to the object which is capable of handling this. This is the basic idea we do here. And as I said, this can be completely generated. So we don't have to deal with that. The only thing we have to do is to provide the behavior for the corresponding non-terminals. Here, just a small example that you have an idea how to do this. Here's the interpret method for the multiplication expression. Here, a multiplication has two sides, left and right. So what you do is you get those sides, evaluate them. Could be as easy as a number, 5 for example, but could be more complicated expressions like 2 plus 4 minus 1 or something like this. So before using this result, of course, you have to evaluate this. So yeah, you call the respective evaluate method, and once you have the values, you just have to do the actual multiplication. It's a little bit more complicated than that because sometimes it depends on the return type. In the multiplication, you only have to check for numeric values, but if you think, for example, of an addition, when you add something to a string, the result becomes a string and so on. Okay, but this is basically what you do when implementing an interpreter. Despite, as I said before, for the multiplication, you wouldn't do this anymore. That's provided. One small addition also to the concept provided in the book is, well, the book just presented the concept and said, okay, everything has return value int, because it's easy and it suffices to show the concept. No doubt, but we need something more general because we want to cover general modeling languages. So we provide this generic value interface, which has several realizations: Boolean, int, double, string, and also some general object value. And well, this generic interface is simply kind of a surrogate just to handle arbitrary types, but also comes with usability methods just to check the type and access the type pretty easy. Okay, now let's have a little example or a little demo. What I did here is I constructed a small grammar for a calculator. And yeah, I called it MontiCalc because yeah, it's a calculator, and when you develop a language in MontiCore, you usually put the prefix Monti before it. Don't ask me why, we just do it. What you see here, I incorporate lots of languages, and then only implemented like 3 lines. Even if you're not familiar with this kind of syntax, it's pretty easy. You have the root node, which consists of several calculation commands. A calculation command is either a variable declaration, an expression, or a statement, which are all imported from here. So I don't care about that. There's only one addition I made. This is this print statement, just because I wanted to be able to show something, so I developed this print statement which can output the value of an arbitrary variable. Okay, And now let's go to the actual application. This is, I integrated the language inside this small web app. And, well, we can just try things out. So we can type 5 plus 3, evaluate it. Here it's the display of the last computation, and we have the result 8. I hope you can see this is a little bit small. Maybe I can zoom a little bit. Yes. Okay. So what you can also do is, I don't have this on these buttons there, but I can type here, as I included arbitrary expressions. I can also do 5 plus 4 times 10 and evaluate this. It also work. And what I can also do is, I said it before with type conversion, if I have something like hello world plus 4 plus 6, I get hello world 46, because this is how it works. It's evaluated from left to right, and then, well, it's simply a string. Nevertheless, something like having the multiplication before the addition, it's simply in the interpreter of the expression language, so we don't have to care about these things. Yeah, but I also included variable declarations, so let's do something more sophisticated. Let's give me 3 variables. Something like this. Now I hit evaluate, but just to have free space so you don't see any result here. It's intentional. So let's say A is 4 times 5, and B is like 5.5. I don't care. So now I have assigned some values, and let's say C is now, well, let's make some distinction. If A is greater than B, then C is yes. Otherwise, C is no. And because I want to have a result, I now print C. If I don't have any typos, now we see the result is yes, because with 20, A is way greater than B. Okay, so much to the basic calculators. But in the beginning, I promised you or showed you an automaton, so let's have the same thing with an automaton. Maybe it's too small to read, but it's basically the same automaton I had on the slide before. So it's a pretty simple machine. Its initial state is off. It can be switched on to an operating state. It starts producing parts, increasing the number of the parts, and while it's producing, it's also increasing the corresponding temperature, because when you're working, you're heating up. When the heat is too high, you go in the cool down state, where you start the cool down phase, and when it's cold enough again, you continue producing. So long until the number of produced parts is 15. So pretty easy, but suffices to present how we interpret it. This is the actual textual model, because in MontiCore we are dealing with textual DSLs. This is just a graphical representation I added for you, but basically what we do is operating on these textual models, and these are also processed and then further analyzed with its AST. What we also see further down here is just the variables which are there, number and temperature. We start with somewhat the room temperature and no produced parts. And we can now fire this up. And you see, okay, after the first step, we switch this thing on and are now in the operating state. So let's go further. Now, every time I hit this, the number increases and the temperature also increases with respect to this random number between 3 and 7. So yeah, I can do this several times now until I reach a temperature which exceeds 65. Now I'm in the cool down phase. So yeah, we just wait for the temperature to go down again. Then you see, okay, here now we are taking the next transition to operating again and continue producing parts. So we go on and on and on. Here again, we exceeded the temperature, so another cool down phase. Just skipped through this. Then one last time we switch to the operating state. We have 14 parts produced, so one time more And you see here, okay, 15 parts are produced, so the next step is switching the machine off again. Pretty easy example, to be honest, but it shows what we can do there. So with the interpreters, we could also go a little bit into debugging models or debugging the execution of models. And yeah, this is basically what we're currently delving in. So coming already to an end with the presentation, what we are currently doing, we have implemented several basic interpreters for, well, a few of our sub-languages, so basically for some statements, expressions, and for the literals. However, of course, there is more work to do. So currently we are just working on extending the library such that we have for all the language component libraries we have also an interpreter which we directly can provide within this library. And also, we are working on some additional usability issues like, for example, when you're a language engineer and want to have some kind of type instance relation within your language. It's possible, not that often the case, but it might happen. You can do this with this infrastructure, but you have to implement a lot. So basically, we want to add some usability support for that just to make this easier to implement. And this brings me to an end. Thank you very much.
So, plenty of time for questions. Yeah.
Thanks for the talk, Nico. Your approach relies on the fact that we implement interpreter as a visitor pattern. The question is, can you implement every interpreter as a visitor pattern? Or are there limitations?
Well, answer is, of course, always it depends. But when you're generating the whole infrastructure of a visitor, you usually come with some basic navigation like depth first analysis or something like this. You cannot do this here just because for expression this works perfectly fine, by the way, but even when you start with the automata, you have to deal with, okay, I'm in that state, now I have to go with the transition to the other state. Here you cannot rely on a default climb down strategy. You can implement it within the interpret method, so it's just a visitor with extraordinary navigation, so it is definitely possible. Also with in combination with the symbol table, what I said in the beginning, every problem we have we solve with the symbol table because it allows this cross-referencing. So actually this is what I did here when implementing this interpreter. I just looked in the symbol table, okay, what's the next state concerning to the corresponding transition? Okay, that one, so I just navigated there. So yes, but it's not that you can always follow a default traversal strategy.
But then when you compose interpreters in different languages, can it happen that they have like a state when they break each other? It's not consistent, so can they influence each other?
I would claim when the languages or language components themselves are conflict-free, this won't happen, but I don't take this for 100% sure. If you have an idea how to break it, reach out to me.
Formal methods are called research about composability of behavior specification and how you can compose them back so that they don't clash. But it's
yeah. So of course, side effects are always possible, but then we could argue whether they are intentional or not. But I would guess the interpretation of the part itself should not be affected.
Well, thanks for the talk, by the way, Nico. I had a question about the types. Is there also a way to check them?
Which types particularly?
To the section of the slides where we were,
That one?
2 more forward, 1 more forward, 1 more forward. Forward. Okay, it was when you had all the compositional aspects.
Ah, okay.
But on the left-hand side, you have all your types. And I didn't, maybe I missed it, but I didn't hear anything about a type system also for checking those types.
Yeah, okay. You didn't miss it, I just didn't tell you. So when we start the interpreter, we consider our models to be well-formed, and to the well-formedness there also belongs that the types are correct. So we have a type checking mechanism in MontiCore, which a colleague of mine works on. So we also provide this for all the sub-languages, which can be employed by our context conditions. So first of all, after parsing the textual model, we run our context conditions, sometimes in several loops, but don't care. And also one part of this is the type checking. So when we start the interpretation, we assume our model to be well formed and also that the types are correct. And maybe your question is aiming at that. I omitted it here, but in fact, in our implementation of the interpreter, we also not only rely on the types here in the result, but we rely actually on the types which were derived for the AST nodes for the specific from the specific type system.
Thanks, interesting, Tom. Maybe I missed that, but do you have support for language restriction where you're inheriting something? For example, you want to inherit compositional language, but you only want a part of that language.
This is a very good question. Usually what we do is, first of all, it also depends on how many parts there are. If you just want one part of a language with 20 parts, you have, of course, to think of, is it worth it? But usually when we do so, we have the case that, okay, I want these 18 parts and maybe not these 2 parts, and then we just explicitly exclude them via context conditions. So this is these are also implemented in terms of a visitor. So they are automatically executed on the AST, just traversing once, and when you reach a node which is of the type production I definitely don't want, then it throws an error and says you don't. Yeah.
In the grammar, and on the behavioral part, you're overriding stuff. You're changing.
On the behavioral part, I can actually incorporate the complete interpreter because I made sure beforehand I will never reach such a node.
Okay, thank you.
Problem.
Yes, I wonder, does your extension mechanism also work? Because you show that you can have an expression, but when you reach a certain sub-expression of that expression that is of a type of node that you haven't taken into account, you sort of fall back to the one you called it. But I mean, it can return a type which is not valid at that position from the perspective of.
Yeah. So in complete general, you're right. So this can happen. In fact, it didn't happen to us, but what is actually a problem? So as you see here, we provide some types that, well, are covering the basic types. And for our purpose, we said, okay, for the terms of modeling, we are fine with them. But what is actually a problem? We have ideas, but we haven't solved it, is actually this object value, because you're not always dealing with just primitive or basic types, so to say, but you can have some type which is called timer or something like this, which might happen actually. So here we are currently working on providing more support to incorporate these more seamlessly. Currently, you can do this via lots of ugly typecasting and so on. We don't want to do this, but you're right. So this is something we have to work on.
For instance, we have just added time-dependent computing.
Mm-hmm.
And so we have normal expressions, but we now can substitute variables in them which don't deliver a number, but just a number for every point in time.
Yeah.
So then you have to repeatedly do the expression interpretation for multiple points in time.
Mm-hmm. Just out of curiosity, I'm returning the question. Are you doing this continuously while further interpreting, or is this just I do this 100 times and?
Well, we basically derive a function from the expression,
Mm-hmm.
and then we lift that function to the time domain. So it's
Okay.
difficult to do.
Mm-hmm. Yeah, to be honest, we're not there with these interpreters. Maybe in a year.
Okay, so let's thank Nico again.